This video considers quantum-accelerated Monte-Carlo methods. Hence, we first review what are Monte-Carlo methods. We are given a sample space of n bit strings. The number of those strings is 2 to the n. The number of different strings I can have is 2 to the n, which I define as capital N. I'm also given a probability vector that is a vector of entries between 0 and 1 of dimension capital N, where the elements of the vector sum up to 1. So it's a normalized probability vector. In addition, I'm giving a sampler for the probability vector. What the sampler can do is output a bit string with probability p of x. Now I'm also given access to a function, a random variable, that takes as an input one of these bit strings and gives some real number as an output. So this could be, for example, the payoff of some financial derivative. Now we can define a few quantities that help us for the rest. We can define the mean of this random variable, which is the expectation value using the probability vector of the function f. It's simply summing over all bit strings p of x times f of x. In addition, we can define the variance sigma square, which is the expected mean square difference. So expected f minus mu square. Our task is now to output some mu tilde such that it is close to our mean mu for some epsilon greater than 0. And that output has to be close to epsilon with high probability, say 99%. The solution to this problem is Monte Carlo. We use our sampler to sample k bit strings from the sampler and form our estimator for the mean, mu tilde. So we use our bit strings, evaluate the function for each of these bit strings, add them up, and divide by the number of samples. We can study this estimator. For example, we compute the expectation value of mu tilde, gives us actually simply mu. So it's an unbiased estimator. In addition, we can compute the variance of mu tilde. It turns out to be sigma square over k. It turns out that the number of samples k that we have to choose is at least 100 sigma square over epsilon square. If we choose k like that, then by Chebyshev's inequality, we can show that the probability that our statistic, our estimator, is close to the mean is greater than epsilon. So the failure probability is smaller than the variance of our estimator divided by epsilon square. If we plug in the variance that we've computed here, sigma square over k, we plug in this lower bound for k, we obtain 1 over 100. So this is the failure probability. So that translates to a success probability of 99% for getting an estimator that's close enough, that's close, epsilon close to our desired value. We can look at a simple example. Take sigma to be 1. Say we want an accuracy epsilon to be 10 to the minus 3. If you plug in these numbers, then we obtain that the number of samples has to be around 10 to the 8. This is 100 million samples. of course, a lot of samples, so and in some cases, accessing the sampler can be very inefficient. So, however, this has been shown to be optimal in the settings if we don't make any more assumptions. Hence, the big question is, if we make further assumptions that we have access to a quantum computer, can the quantum computer help us improving the number of samples? Now, we're going to review quantum-accelerated Monte-Carlo methods to provide an answer to the question if quantum computing can help for the classical problem. For this, recall that we have a sample space omega, a probability vector p, and in the classical setting have a sampler that provides samples from p. Also recall that before in the classical setting, we needed a number of samples that was about 1 over epsilon square if sigma was taken to be 1. Now we make further assumptions. First, for simplicity, we restrict the function to the interval 0, 1. Second, we assume the standard gate model of quantum computing. For this, Nielsen and Chuang provide a great introduction, and also other resources on this webpage. In addition, we have an n-qubit state preparation circuit that prepares the probability distribution P as follows. I have my circuit, I let it act on n qubits, and it will prepare the following state. I have a sum over all bit strings. I obtain an amplitude that's the square root of the probability px, and I have a superposition of different bit strings x. So this is one key assumption. This is the analog of the quantum sampler. Secondly, we have an n+1 qubit controlled rotation circuit. What can that circuit do? As I said, it's n+1 qubits, so we have our n qubits and also another one. And say these n qubits are in the state in some state x. Then we rotate the ancillar qubit by an amount that's proportional to f of x as follows. So the ancilla is put in a superposition state with an amplitude square root of f of x and the corresponding amplitude for the one state of square root of 1 minus f of x. So what can we do with these controlled rotation circuit and the state preparation circuit? How can we use these circuits to get our desired expectation value? For that, let's just see how these circuits act on the computational initial state. So you have my n qubits here and 1 qubit here. And to use these two steps sequentially, what we will obtain is sum over x, square root of p of x, x, and again our rotated ancilla. Now, if on this state, let's call it psi, we measure the following observable. So we have the observable, a projector P, that's defined as the identity matrix on n qubits, tensor the projector onto the 0 state of the ancilla. If we evaluate this projector on the state psi, so we measure this projector, then it's easy to see that actually that we obtain mu. However, we're not at this point not obtaining any quantum speedup. For a quantum speedup, we refer to the literature, to the famous result by Brazin, Hoyer, Mosca, and Tapp from 2000. In this exact setting, there exists a quantum algorithm that outputs a mu tilde that is close, epsilon close to our desired mu, using these circuits U, P, and UR for 1 over epsilon times. That is, of course, that is a quantum speedup that could be a quantum speedup over the classical case that goes as 1 over epsilon squared. Let's look at an example. Again, we have, if we want to have epsilon as 10 to the minus 3, that would give us that we need to access these circuits 1,000 times. Hence, that is much better than what we had before, where we had 10 to the 8 times, where we accessed our classical sampler S